So hello everyone, and thank you for coming to our virtual tutorial. And today we're going to talk about ways to determine the optimal anomaly detection method for your time series application. And this is a hard problem because the existence of a single anomaly detection method that is optimal for all domains is a myth. So to begin tackling this problem, we need to understand some background material first. And we'll start with defining terminology like what even is an anomaly and why this problem is so difficult. And we'll also talk about several very common characteristics that one can encounter in time series data and how we might detect them using Python and R. I will then show some useful resources for time series data before jumping into some anomaly detection methods themselves and how to evaluate their performance. And finally, we will conclude with some human-in-the-loop methodologies to greatly reduce annotation efforts and reduce false positives. So Tim already kind of gave some background about us, but a little extra. I'm also a research scientist at Vera Intelligence Self-Service, a provider of conversational AI systems for enterprise businesses. And Ian is chief scientist, so yes, he is my boss. And we do a lot of work in improving chatbots and intelligent virtual assistants that are typically used by companies in the customer service domain. And our work happened to intersect a little bit with time series analysis, which is what kind of inspired us to give this tutorial. So now that you know a little bit about us, we're going to proceed with understanding some background material first. So we work in the context of univariate time series. And a time series is a sequence of data points indexed by order of time. And time series are used in almost every field: intrusion and fraud detection, tracking key performance indicators, the stock market, and medical sensor technologies. And you create a time series when you track the daily height of ocean tides, the counts of sunspots, or the closing value of the Dow Jones Industrial Average. And one important use of time series is for the detection of anomalies. So an anomaly in a time series is a pattern that doesn't conform to past patterns of behavior in the series. And its detection is vital for ensuring undisrupted business, efficient troubleshooting, or even in the case of medical sensor technologies, lower the mortality rate. Your bank identifying that an out-of-the-ordinary purchase was in fact fraudulent is a prime example of the importance of anomaly detection. But in practice, anomaly detection is generally much more nuanced and complex, which can make it daunting to undertake. So why is anomaly detection so hard? So first off, what is defined as anomalous may differ based on application. The existence of a one-size-fits-all anomaly detection method that's optimal for all domains is a myth. In addition, if I include some contextual variables, for example, that may change initial perceptions of what even is anomalous. So suppose I own a bike rental company, right? And on average, the number of daily bike rentals is 100, and one day it's only 10. And that might initially appear anomalous, but if it's a cold winter day, that's actually not so surprising. And in fact, it might appear even more anomalous if there were 100 rentals instead that day. So anomaly detection also must be done often on real-world streaming applications, so it has to be efficient. And strictly speaking, an online anomaly detection method must determine anomalies and update all relevant models before occurrence of the next time step. So a good example would be like self-driving cars. When deer's on the road, this is anomalous, and the car must quickly identify this and react appropriately. Depending on the needs of the user, it can be acceptable to detect anomalies periodically, but regardless, efficient anomaly detection is vital, and that presents a challenge. It's also unrealistic to assume that anomaly detection systems will have access to thousands of tagged data sets. In addition, it can be very easy to encounter anomalous or not anomalous behavior that was not present in the training set. Also, as an anomaly is a pattern that doesn't conform to past patterns of behavior, non-anomalous data tends to occur in much larger quantities than anomalous data. And that can present a problem for a lot of traditional machine learning classifier approaches to anomaly detection, as the classes are not represented equally, right? So like an accuracy measure could present excellent results, but the accuracy is only reflecting the unequal class distribution in the data. And that's called the accuracy paradox. So for example, if I have 100 data points and only 2 anomalies, the classifier can say, hey, every point is not anomalous. And then you get 98% accuracy and you feel really good about yourself, but you actually didn't really do a good job. It's also important to detect anomalies as accurately and efficiently as possible. But minimizing false positives is also of great necessity to avoid alarm fatigue. And alarm fatigue can lead to a serious alert being overlooked and wasted time in checking for problems when there are none. So there was one study done at the Johns Hopkins Hospital where they identified 59,000 alarm conditions, 59,000, during a 12-day period, or basically around 350 alarms per patient per day. And research shows that up to 85% of those hospital alarms are false positives. So with all these alarms, it's pretty dang easy to understand why nurses and doctors suffer very frequently from alarm fatigue. And finally, there is a massive wealth of anomaly detection methods to choose from out there. Every year, you're going to see more and more papers published on it. So how do you make your choice? What anomaly detection method should I choose? So because of all these difficulties, we decided to tackle this problem by focusing on the characteristics the time series has. So in this tutorial, we're going to evaluate a number of anomaly detection methods on several time series characteristics. We will show which anomaly detection methods are more promising given these characteristics. So for example, if the time series data in a user's application exhibits concept drift and maybe no seasonality, you might want to consider the anomaly detection method Facebook Prophet and not Twitter anomaly detection. We will also highlight the differences between several scoring methodologies. And finally, we will consider a human-in-the-loop strategy to improve evaluation scores and greatly reduce false positives. So this diagram gives a basic architecture for an anomaly detector for a time series. And most of the methods we will cover follow the same basic pattern of filtering out the predictable components of the signal, leaving what we hope looks like white noise and occasional anomalous behavior. We next want to convert the signal into a score that ideally gives us some control to trade off precision and recall. And if this score exceeds the threshold, we alert to an anomaly. So to give a taste, let's walk through a very simple detector that just looks at the mean and variance of the signal computed over a sliding window. We're going to refer to this method as the sliding Gaussian window detector. So for the filtering step, which we saw here, the second step, we're going to use the identity function. To obtain a score, we first subtract the mean and divide by the standard deviation. We can then use the complement of the tail probability of the standard normal distribution to get an anomaly score between 0 and 1. The tail probability is simply the probability that a random variable deviates by a given amount from its expectation. To detect unusually low or high values, this score is computed relative to the low and high tails of the distribution, and the maximum is returned. And you can see how this works in the example on the right. The shaded band shows the range for the signal based on the detection threshold and estimated standard deviation. And note that the mean suddenly shifts, and this would be detected as anomalous, but then over time, the detector slowly adapts. And there's also what one might consider an incorrect detection just before the mean shifts around February 25th. So on the left here, we have a plot of the anomaly score for the time series shown previously, and on the right is the same but plotted on a log scale so it's easier to see. And there's this obvious spike where the mean shifts and then it decays as the detector adapts to the new distribution. And for some signals, this detector might work okay, but for some signals that show strong temporal dependency, we may be able to do better by taking those dependencies under account. So now that we have gone over an example of the signal processing flow, I'm going to give an overview of some common time series characteristics that a better anomaly detector may need to account for. So as we want to choose the anomaly detection method based on the characteristics the time series possesses, we will now describe these characteristics. And note that this is not a comprehensive list. I'm just going to cover some common ones that might appear in your application. So a time series is stationary if the mean, variance, and autocorrelation structure are constant for all time. And an autocorrelation is simply the correlation of a signal with a delayed copy of itself. That's why I bolded this auto here. And a white noise process, right here, is stationary, for example. And many anomaly detection methods out there require the time series be made stationary first as a kind of pre-processing step. So most time series you're going to encounter in the real world are not going to be stationary. Many of the characteristics we're going to talk about make a time series not be stationary. So for example, the time series might contain trend. So the mean of the data set is not constant for all time. Or the time series might contain seasonality, which will affect its autocorrelation structure. So we're going to first talk about seasonality. All right, so we will first talk about seasonality. Seasonality is the presence of variations that occur at specific regular intervals. It's necessary for companies to identify and measure seasonal variations within their market to help them plan for the future. So if you're an ice cream vendor, you need to prepare for the decrease in demand for your product in the winter. You can also have seasonality at multiple time scales. In this time series on the right, there is 24-hour seasonality and also weekly seasonality. In addition, though it's not displayed, there is holiday seasonality with a spike occurring every 4th of July. Seasonality can also be additive or multiplicative. If multiplicative, the mean of the data is related to the amplitude of the seasonal behavior. So in this picture, the seasonality looks additive, for example. In the coding examples we're going to go over, I will show you guys an example of multiplicative seasonality. Also, this picture makes it pretty obvious we have seasonality just from looking at it, but this is not always super obvious. So if I told you that the time series here on the left had seasonality, it might be hard to tell just from looking at the time series. And obviously you could say, oh, I'll just play with the scaling of this picture and I can see it better. And that's possibly true, but it's actually highly recommended that we look at something called an autocorrelation plot. And this plot displays the correlation for time series observations with its legs, which are observations from previous time steps. So a time series that exhibits seasonality will show a repetitive pattern in its autocorrelation plot, like in the right here. And more specifically, the autocorrelation plot's x-axis shows the leg value, and the y-axis shows the corresponding autocorrelation coefficient. So here is the equation for that. For example, at leg 1, we have R1, where k is 1, which measures the relationship between time series values that are only like one step apart. So yt and yt minus 1. And at leg 2, we'll have R2, which measures the relationship between yt and yt minus 2. So basically time steps are 2 time steps apart. And this coefficient is between -1 and 1, and it describes a negative or positive correlation respectively. A value of 0 indicates no correlation. And you can see this blue cone here. and that represents the confidence interval. And values that sit outside of this confidence interval are very likely a correlation and not some sort of statistical fluke. So when data is seasonal, these correlation coefficients on the y-axis will be larger for seasonal legs at multiples of the seasonal frequency than for other legs. So we'll see these repetitive steps, right? So in this case, we actually have a periodicity of 24, because this is actually a time series with hourly time steps, and you can use this autocorrelation plot to kind of see, oh, I have seasonality and what my periodicity is. And as mentioned previously, a time series that exhibits seasonality will show that, but what would be cool is if there was a way we can automatically detect seasonality without looking at pictures, and that's especially useful for someone who doesn't really have the time to look at it or is not an expert. And there are functions out there that can help you with that, although I'm going to warn you, it's not perfect. It's more of like an estimator. And that function is actually in the forecast library in R, and it's called find frequency. And the general idea is that it returns the period with the maximum spectral amplitude of the signal. And that can sound like gibberish, but what that means is we will first convert the time series into the frequency domain. And when we convert it that way, we can do that using something called a periodogram. And it will return the period corresponding to the max value in the periodogram. And don't worry if you got confused by that, we're going to go through step by step how that works. And the periodogram graphs a measure of the relative importance of possible frequency values that might explain oscillation patterns in your observed data. So to create this periodogram, we first convert the time series into a format that can be represented as a sum of sine and cosine waves. So basically, I can rewrite my time series to look like this equation. And note that this equation is working under the assumption we have an even number of distinct values n in the time series. And there's a separate equation for the case when you have an odd number, and you can just check that up online. It's beyond the scope of this. And these fractions j over n are harmonic or whole number frequencies. And j goes from 1 to n divided by 2. And you want to think of these beta 1s and beta 2s as regression parameters. And estimation of these regression parameters is typically done using fast Fourier transform, or FFT. You don't normally have to do this. You have computer software to do this for you. After we estimate beta 1 and beta 2 using FFT, we can create the periodogram. And in the periodogram, the x-axis is those j over n frequencies, and the y-axis is p, which is the sum of those squared coefficients at frequency j over n. So the periodogram graphs a measure of the relative importance of possible frequency values that might explain the oscillation pattern. So if you have a very large value of p at frequency j over n, that indicates relatively more importance for that frequency j over n in explaining the oscillation in the observed series. And that's in essence what that R find frequency is trying to do. So let's take a quick look here. So we have a time series here on the top left. And I know, and you know, we can just look at this and go, oh yeah, there's seasonality, right? Or if you're not entirely sure, you can also look at the autocorrelation plot here. And if you're saying, oh, what is my periodicity? How many time steps until it repeats itself? Well, I can graph the periodogram, which is right here, and see a massive spike in P at frequency 0.0025-ish. And recall that periodicity and frequency have an inverse relationship. So the periodicity is around 365, meaning we have yearly seasonality. So we're going to go ahead and play around with detecting seasonality using Python and R, using IPython notebooks. And I have to do it this way because for some reason, Zoom wants to put things right on the top, kind of blocking my view. So I'm going to go here. And once again, you can access these notebooks at the links that Ian has provided previously. And so basically, If you don't know, IPython Notebook is an interactive computational environment where you can combine code execution, text, LaTeX, and plots. And you can divide the code into cells and execute each cell individually. So we're going to create some autocorrelation plots and periodograms for several time series using pandas. And pandas is an open source Python library providing high performance, easy to use data structures and data analysis tools. And we're also going to explore the R find frequency function. So here in cell 1, I just simply import that pandas library I tell you about. Then I load a data set that is inside the data folder of exercise 1 that's provided in that link. And this data set specifically contains the daily minimum temperature in Celsius in Melbourne. And this creates something that's called a data frame object, where data is aligned in a table fashion with rows and columns. And we can look at the first 5 rows of the data set using the head method. However, when I load the data set, the type of the dates column is a string, and Pandas has a lot of nifty tools we can use if we can help it realize that the date column actually contains dates. So I'm going to do that using the toDateTime command. Note that I have to tell Pandas the format the date is in, right? And I have that because I use the head command here, so I know how it's supposed to look like. Depending on your data, you're going to have to specify the string, and that's what this URL appears for. So although the CSV that we have loaded actually has the dates sorted already from earliest at the top to latest at the bottom, not all CSVs you get might be so nicely sorted. And since we told Pandas that the date column has dates, we can use the sort values command to sort the data by date. I'm going to plot the time series now using matplotlib, Python plotting library, and I load it here and plot the time series. And this is one picture that we saw earlier. And so seasonality is obvious, right? But let's plot the autocorrelation for fun. So recall from our slides that the autocorrelation plot plots these autocorrelation coefficients. So for every leg k, it has its own autocorrelation coefficient rk. There are better ways to do this, but first I want to show you that I can individually calculate every RK using series objects from pandas. So I instantiate a panda series from the values in the time series, and then use the autocor method to compute the leg K autocorrelation. So basically this method computes the correlation between the series and like a shifted version of itself. And I just iterate from 1 to 1,000 K legs. And then plot the legs here, the Ks, versus the autocorrelation coefficients RK. So that is a very basic way of making an autocorrelation plot. And you can see that repetitive behavior. But I want you guys to know that there are functions out there that will directly plot it for you. So that way we don't have to go through this. There's the plot ACF function from stats models. Stats models is a Python library that provides classes and functions for the estimation of many different statistical models, as well as for conducting tests and data exploration. So here's how us using that looks like. So once again, values outside of this cone are very likely a correlation and not some sort of fluke. So you might be wondering, why does this blue cone get bigger and then taper off, right? Well, let's think about what this autocorrelation plot is telling us. Suppose we were taking blood pressure measurements over time. So it would make sense that blood pressure measurements taken between 2 days would be more highly correlated versus blood pressure measurements taken between like a 5-year gap. So typically the autocorrelation should go to 0 as you go further out in the legs. And the confidence interval is also taking this into account by becoming fatter the farther out in legs you go and then tapering off. It's less likely to have significant correlations the further out you go. So by default, the number of legs shown is the max allowed, and the confidence interval is 95%, but you can easily change that. So in this case, I'm like, all right, I just want to look at first 500 legs, or in this case, oh, I want to look at the 99% confidence interval instead of the 95. So looking at this autocorrelation plot, we notice that this wave repeats itself every 300 to 400 time steps. And it's actually 365 as we are seeing yearly seasonal temperature patterns. We're going to see if we can get a more exact number here using periodograms. And a periodogram graphs a measure of the relative importance of the possible frequency values that might explain these oscillatory behaviors in our data. So the x-axis is the frequency j over n, and the y-axis is this sum of the squared coefficients at the frequency j over n. And we can do this. We don't have to do f of t by hand. Thankfully, we have computer software to do it for us. I'm going to use SciPy's periodogram function, which returns the x-axis and y-axis values f and p respectively. F being the frequency, the j over n. So here, I'm going to plot f and p, and you can see that huge spike in p. And remember that a relatively large value of p at frequency j over n indicates relatively more importance for that frequency. So here I just go, okay, what is my max index? I'm like, okay, it's around 0.0027. Frequency and periodicity have an inverse relationship. So kaboom, here we go. I have my periodicity of 365. We're going to go ahead and look at another data set, the number of airline passengers per month. And from looking at this time series, we actually have this nice upward trend and evidence of seasonality, right? We have this oscillatory behavior, and not just, additive seasonality, we have multiplicative seasonality because the amplitude of these waves is related to the mean of my data. The larger the mean is, the larger these waves. So I'm going to go ahead and plot the autocorrelation of this time series, and we see evidence of that repetitive behavior, right? And this autocorrelation plot looks a little different from the autocorrelation plot we had of the temperatures. The slow decrease in the autocorrelation as the legs increase is actually due to the trend here. If you actually remove the trend first before making the autocorrelation plot, it would probably look a little different. But when data has a trend, the autocorrelations for small legs tend to be large and positive because observations nearby in time are also nearby in size. So the autocorrelations of trended time series tend to have positive values that slowly decrease as the legs increase. And here we plot the periodogram, and notice actually several interesting spikes for P. So I'm going to go ahead and look at that first big spike. And when we do that, we see that the frequency corresponding to it is 140. Frequency corresponding to it, if you take the inverse, you'll get a periodicity of 144. Let's go ahead and take a look at that second spike. So here, I'm just zooming in on that second spike. And I have this red vertical line that I drew, which crosses the point of that second spike. And this corresponds to a frequency of 0.0834, which honestly gives us a periodicity of 12. So to understand the significance of the higher frequency peaks, remember that the periodogram is calculated by modeling the time series, right, as a sum of cosine and sine functions. And periodic components that have the shape of a sine or a cosine function, meaning that it's sinusoidal, show up in the periodogram as single peaks, kind of like what we had going on here, right? But periodic components that are not sinusoidal show up in a series of kind of like these equally spaced peaks of different heights. So what this means is that the periodic component is not super sinusoidal. And we're just seeing these evenly spaced peaks for that reason at multiples of 12. So now I'm going to go ahead and try the R function, find frequency. And I'm going to use the Python library rpy2, which provides a nice Python interface to the R language. So I import the library forecast, which contains that function find frequency. And I'm going to say this right now, it is very odd that a function named find frequency does not actually return the frequency. Find frequency returns the periodicity in this case. Don't know why they chose to name it this way, but that is the way they chose to name it. But keep that in mind. So here it actually returns 12, which is that dominant frequency, the one we're going to see a ton of multiples of here. And also note that one weakness of fine frequency is that it only returns one periodicity. So if you have a time series with multiple seasonalities, and I'm not saying like these multiples, okay? Fine frequency is only going to help you find one periodicity, which in this case was 12. If there is no seasonality, fine frequency is just going to return 1. So in summary, we have played with the autocorrelation plot, the periodogram, and fine frequency function in R. And the autocorrelation plot displays the correlation for time series observations with its legs. The periodogram graphs a measure of relative importance of possible frequency values that explains oscillation patterns in the data. And the R fine frequency function returns the dominant period, not the frequency of the signal. Okay, so let's go back to some slides. So other behaviors for time series include trend, where the process mean can change gradually over time. Because the mean is not constant over time, this means this time series is not stationary. And we can easily detect that trend exists in this picture, but other times it is not very obvious, just like seasonality. How we statistically determine if trend is present depends on the kind of trend we have. And there's going to be two kinds of trend we're going to talk about, stochastic and deterministic trend. And before I describe these trends, just a little refresher on what it means to be deterministic versus stochastic. So in deterministic models, the output of the model is fully determined by the parameter values and the initial conditions. Stochastic models, though, possess some inherent randomness. So you can have the same set of parameter values and initial conditions, and you can have different outputs. So basically, for stochastic trends, the mean trend is stochastic. And stochastic trend is removed using differencing, where we subtract a previous observation from the current observation. And because it is removed via differencing, sometimes people will call stochastic trend different stationary trend. You might see that in papers. For deterministic trend, the mean trend is deterministic. And deterministic trends are removed by detrending the time series, where you find some line that best fits the data and then subtract it from the data. And that's why they are sometimes called trend stationary. Visually speaking, deterministic and stochastic trends can be very similar looking. However, if you want to create a stationary time series, which is necessary for a lot of anomaly detection methods, you will need to remove the trend. If you difference to remove a deterministic trend or subtract a line of best fit from a stochastic trend, you actually might not remove the trend. Thus, it's really important to tell what kind of trend you have. So there are many tests for detecting these kinds of trends, but I'm going to use two easy ones in our coding examples. You can go check out the literature for other ones that might be better. But basically, stochastic trend, I'm going to detect it using the augmented Dickey-Fuller test, whereas the Cox-Stewart test can be used for detecting deterministic trend. So we're going to go ahead and look at a IPython notebook. Back. Oops. So once again, we're going to use pandas and matplotlib and rpy2. And this is because some statistical tests we're going to run are only available in R. I'm going to load some data from our exercise 2 data folder. And this one gives us the daily total female births in California in 1959. And I'm just looking at the first 5 rows using the head command. And I convert the date column to type date time and plot our time series. So does it look like we have trend in the data? So you might think, well, there might be some going on here. But even then, that can be kind of tricky, right? And even if you think there is trend, it'd be pretty hard to know, like, is this stochastic or deterministic? So we are going to first try testing for stochastic trend using the augmented Dickey-Fuller test. So right here, the null hypothesis is that there is stochastic trend. And the alternative is that there is no stochastic trend. So I'm going to use the augmented Dickey-Fuller test from stats models. And I'm going to use a p-value of 0.05 as a cutoff, but honestly, that's just user choice. Since our p-value is less than 0.05, we reject the null hypothesis. There is no stochastic trend. However, there could still be deterministic trend. And we're going to test for this using the Cox-Stewart test. So the null hypothesis here is that there is no deterministic trend, and the alternative is that there is. And be careful because the order of hypotheses is different from augmented Dickey-Fuller. Unfortunately, the Cox-Stewart test is not available in Python, but it is in R, and that's where I'm going to use RPy2. So I use the WebR library for statistical computing, and I run the Cox-Stewart test. And in this case, the p-value is less than 0.05, so there is deterministic trend, and how we're going to remove it is by subtracting the line of best fit. And I will acknowledge that there are many ways you can find this line of best fit. We simply don't have the time to go over every single method, so I'm just going to do a very simple method using scikit's linear regression. So here, I'm importing that linear regression from scikit-learn, which is a free software machine learning library. And I fit a linear regression here and also just predict over that same data set. And in this picture, we plot the actual data, which is the blue, versus the prediction, which is the orange. I then detrend by subtracting this line of best fit from the time series. So here's that time series again, but detrended. So let's try the Cox-Stewart test on this detrended data set. Now the p-value is above 0.05. We do not reject the null hypothesis of there not being any trend. Note that I'm saying we don't reject it. I'm not making any like straight up conclusions here though on there being trend or not. Here we try another data set that we actually played with in the previous exercise, the airlines data set. Okay, this is something that we saw before where there was that increasing trend and that multiplicative seasonality. So I run the augmented Dickey-Fuller test here, and the p-value for the data set is greater than 0.05. We fail to reject the null hypothesis, where the null hypothesis is that the time series has stochastic trend. So possibly we might have stochastic trend. Now I go ahead and try the Cox-Stewart test using R, and the p-value is less than 0.05. We reject the null hypothesis, so there is deterministic trend. So at this point, what do we know? We know that there is deterministic trend and possibly stochastic trend. So we're going to go ahead and do two things here. We're going to difference and detrend. So I'm going to detrend by looking for that line of best fit. So once again, I am looking at using scikit-learn's linear regression, create this line of best fit, subtract that line of best fit, and now I'm going to do the next thing, which is differencing. So we can easily, well, hang on, differencing is taking the difference of the observation of a particular instant with that of a previous instant. And actually, pandas can do this very nicely when we're playing with the autocore method in series, where we can kind of just easily shift a time series, right? So I'm going to go ahead and use pandas to create a lagged version of the data set for us. So I first create a convert my detrended values to a data frame and then shift it. So obviously, because I'm shifting it, the first value here is going to be a nan. I then subtract the two to create a difference data set, and then I plot it. However, when I do an ADF test on this, I still have a p-value above 0.05. Don't be concerned here, because actually sometimes we need to difference multiple times in a time series. So here I'm going to go ahead and difference one more time by shifting again and then subtracting. And now the p-value for my ADF test is less than 0.05. I know it shows a bunch of zeros here. But if I were to actually print out more, you would actually see a very small value. Now, the p-value is less than 0.05, would reject the null hypothesis. There is no stochastic trend. We have differenced and detrended. So what does the Cox-Stewart test say? And previously, before detrending, we had a p-value of less than 0.05, meaning we had deterministic trend. But now the p-value is greater than 0.05, meaning we don't reject the null hypothesis of there not being any trend. So that's just an example of how you could go about removing the two kinds of trends that are very important in time series. And I want to emphasize one more time, you don't have to use the ADF and the CS tests, the augmented Dickey-Fuller and Cox-Stewart. There's other ones like the KPSS test, and they're worth checking out. But I chose these tests because they're very simple and kind of got the point across. So let's go back here. So other behaviors that may be exhibited by a time series include concept drift, where the definition of normal behavior changes over time. And initially, a concept drift can trigger an anomaly, but an adaptive system should quickly determine that a new pattern of behavior has occurred and is the new normal. So in this time series, the concept drift is a quick drop in the mean of the data. And concept drifts can be difficult to detect, especially if one does not know beforehand how many concept drifts there are. So we can actually use some Bayesian methods to determine if a concept drift has occurred, and we don't need to know how many concept drifts there are in the first place. So let's go ahead and play with that using Python. So what this code is based off of is a paper called Bayesian Online Change Point Detection by Adams and McKay. The link here is on top if you want access to these paper. You can just download the notebooks from the URLs. And in this paper, you don't need to know how many concept drifts there are beforehand. And an implementation of this paper is available on GitHub using T distributions for every new concept referred to as a run. So we're going to be using that implementation. And that's what I'm doing here. I'm loading all the necessary libraries, including that Bayesian Online Change Point Detection implementation. And I'm going to load this data set, which consists of CPU utilization metrics for Amazon Web Services relational database service, and plot the time series. So you can definitely see evidence of concept drift, as well as this huge anomalous spike. And you can read the paper for more details, but the idea is that the time series is divided into these non-overlapping pieces, right? And in between these pieces are change points, which mark the end of a current run and the beginning of the next run. And it is assumed that for each piece or partition, the data within it come from some probability distribution. And the implementation uses T distributions. And the goal is to estimate the posterior distribution over the current run length or time since the last change point given the data so far observed. So here, the posterior probability of the current run's length at each time step can be displayed using a logarithmic color scale. So from looking at these posterior probabilities, there appears to be strong evidence for 4 runs in this data set, and you can also see how long these runs are. As another example, I'm going to make a time series of white noise with mean being 0 and standard deviation of 1. And the posterior probability plot here just shows this solid line. Essentially, it thinks we only have this one run and that it is still going. So that's a demonstration of how one could use this interesting library to find these kind of mean shifts in your data, which is very useful if you don't want to know how many you have beforehand, which is necessary in online settings, right, especially. So let's go back here. So the last characteristic we will consider as an example is missing time steps. And missing time steps may occur in time series due to imperfect sensors and are a frequent occurrence in real-world data sets. So a sensor can break down, several time steps worth of data can be lost, and missing time steps may make it difficult to apply anomaly detection methods without some form of interpolation. However, other methods can handle missing time steps innately. So we have gone over some time series characteristics and how to detect them using various Python and R libraries. And we're going to talk soon about several anomaly detection methods, their strengths and weaknesses, and how to apply them. But before I do that, I want to share some resources for time series datasets. And this first is from Numenta's benchmark repository. And this repository consists of around 60 time series datasets and are annotated for outliers. You can see the annotation instructions in the second link here. And the second resource is the UCR time series classification archive. And the research community generally finds these archives to be a very useful tool. And to date, more than 1,200 people have downloaded this archive, and it has been referenced several hundred times. I'm going to warn you, though, that data may not necessarily be annotated for outliers. Another resource is the time series data library. It's an R library created by Dr. Rob Heinemann, also from Australia, which is where the conference is being held. Sadly, I can't go. I really wanted to visit. Time series data sets are also available on Kaggle, an online community of data scientists and machine learners, which allows users to find and publish data sets, work with others, and enter competitions to solve data science challenges. Okay, so we're going to finally begin exploring some anomaly detection methods. So obviously, there are many, many methods out there, and I will not be able to go over all of them in this tutorial. When determining which method is good given a characteristic, however, we did conduct a lot of offline experiments, and the anomaly detection methods we chose to work with in those offline experiments cover a wide breadth of techniques. So some are probabilistic, such as variational autoencoders. Others are frequency-based, like anomalous. Some rely on neural networks, like RNNs and HTMs. Others rely on decomposition of the signal itself, like Ceramax, STL, and Profit. Don't worry, we're going to be going over some of those. So remember, we started off with a simple detector, right? The sliding Gaussian window detector. And we talked about how in the presence of seasonal variation trend or phenomena like sudden mean shift, it could possibly miss anomalies or raise too many false positives. So now I'm going to cover a few general approaches to filtering the signal in order to account for this. So one of the simplest approaches is to apply one or more rounds of differencing, where you transform the signal by subtracting the previous value from the current value. And that's something we tried out in exercise 2, where we removed some trends, right? Either using differencing or detrending. And if the signal shows like a linear trend, differencing the signal once will remove it. And a second round of differencing can help eliminate quadratic trend. So these plots here on the right show the effect of differencing on the example I used before for the signal processing flow. So the top plot shows the result from running the sliding Gaussian window detector on the original time series. And on the bottom, we applied the same detector to the difference time series. And notice that the range for detected anomalies is much tighter following the initial shock of the mean shift. So an alternative approach for time series that exhibit seasonality and trend is to actually just go ahead and break the signal down into those components. So a popular algorithm that accomplishes this is STL by Cleveland. The paper's right here. And you can guess that S and T refer to season and trend. And the L actually refers to LOES, which is a method for local regression or smoothing. And I want to say that there are actually many ways to decompose a time series into those three pieces: trend, seasonality, remainder. You can look at X11 or seats. I'm showing you STL because it is probably the most famous. LOES means that STL can innately deal with missing time step gaps. And STL divides the signal into these subseries based on a specified periodicity and iteratively updates estimates of the season, trend, and remainder. So for example, if there's yearly seasonality and the time series has monthly time steps, there will be 12 cycle subseries where all January time steps form one series, all February time steps form another series, and so on and so forth. And the hope is that the remainder component will look more stationary and then can be used with a sliding window Gaussian detector. Finally, the STL method also includes an outer loop that helps handle outliers, and it updates a robustness weight that reduces the contribution of these extreme points. So we're going to go over STL using STL plus and R, and there are actually several options for doing STL that you might have heard of. There's actually R's just STL, and also Python stats model decompose function. The reason why I'm specifically using STL plus and R though is that you can actually handle missing time steps. I know that I said STL should be able to handle them innately because of LOS, but unfortunately not all implementations of it may be able to. However, STL plus definitely can. Go ahead, close that. Exercise 4. So here, I go ahead and load all libraries, and this get anomaly scores function uses that simple sliding Gaussian window example we discussed at the beginning of the tutorial. We're going to go over it again in this notebook, and note that this is just a user choice. You might have a different way to come up with anomaly scores given the STL residuals. So STL plus is a R library. So I load RPy2 so that way we can run our code in this Python environment. And I'm using RPy2 slightly differently here because it's sort of annoying to convert the data frame's timestamps to the format R's STL plus wants, starting from Python. So I import the STL plus library and load some temperature data. I import the CSV from the global environment and make the default figure size 5 by 5 inches with 200 dpi resolution. I look at an autocorrelation plot of the data. So previously, maybe this is a little too big, but you can change this in your code if you download the notebooks. But previously I showed you how to make these plots using pandas, right? So you can definitely do that in R2. And the confidence interval is actually these dashed lines now. And the periodicity is 365 like before. So you might be asking, why is it that R's confidence interval looks different, right, compared to Python's? Remember in Python's you had that cone? And the reason is that the variance in R is calculated as simply 1 over n, where n is the length of the time series, while in Python, the variance, they chose to calculate it using Bartlett's formula. So the results in the first begin to first increase, then flat. That's the reason why, because they use a different formula for variance. So we use STL plus now, right here, and I'm going to go over some of these parameters. Note that there's a ton. I'm just going to go over just some of the important ones. So NP here is the periodicity, which we set to 365. And we know it's 365 because we looked at the first exercise and we played around with the autocorrelation plot, periodogram, and fine frequency. Here I set outer to 1, which is a good idea to help your time series be a little bit more robust to outliers. And this S window, periodic, S window controls how rapidly the seasonal component can change. So small values allow for more rapid change. If seasonality is more constant, use a larger value. So I set the seasonal window to be periodic because I think the seasonal component is going to be identical over time. And that's because, you know, this is temperature in Australia, and I think that's going to be pretty constant over the years. For more details on how to determine S window in cases where you think there might be more seasonality changes, it's worth reading over that Cleveland paper in my slides, which shows how one can actually calibrate S window. And due to time, we're not going to go over that portion. Not shown here is also a parameter called t.window. And t.window is similar to s.window, but it's for trend and basically controls how rapidly trend can change. So once again, smaller values allow for more rapid change. T window is the number of consecutive observations to be used when estimating the trend cycle. So unlike S window, which has to be user specified, T window does not. So here I plot the STL components. So the original time series is up here, it's called raw. Then we have the seasonal component, the trend component, and the remainder component. So notice how the remainder component looks a lot more stationary. This is the kind of stuff we want to actually use in a lot of our anomaly detection methods. So I analyze the autocorrelation plot of those residuals. And indeed, more legs are within the confidence interval. So I decided to write the remainders to a CSV for later analysis. Now I'm going to do this again, but I'm going to remove some data points in the temperature data set. And I'm just doing this because I want to demonstrate some of the power of STL+. So I plot the autocorrelation plot again, and note here that I include this argument, NA action equals NA pass. This is something you have to do if your time series has missing time steps. Don't just delete the rows in your CSV that have nans in them, right? This will actually cause you to underestimate your autocorrelation values. So then I run STL+. It can actually deal with missing time steps innately, hooray. And then I plot the STL components, and I plot the autocorrelations of those residuals, once again, using NA action equals NA pass. Because if you have a NAN in your data, then you're also going to have NANs in the corresponding residuals. So be careful, although STL+ can deal with missing time steps innately, the residuals will still have NANs in them. So if I was going to use, see here's some NANs, so if we were to use some anomaly detection method like that sliding Gaussian window on the residuals, we would need to do some form of interpolation still on those residuals. So remember I wrote the CSV, wrote to CSV the remainders, not the remainders with the missing stuff, but the remainders from the first example in this notebook. I'm going to go ahead and load those and then plot them here in Python. And to get from STL residuals to a score, I'm just going to go ahead and subtract the mean and divide by standard deviation as like a normalization step. So here's the plot of the normalization. And I'm just going to look at the first 200 values so we can just see the time series and anomaly scores better and just sort of compare them. So I obtained the anomaly scores using the get anomaly scores function. More specifically, we use the complement of the Q function of the normal distribution to get an anomaly score between 0 and 1. And I'm just going to look at one direction for simplicity. And the survival function, given an input x, returns the probability that another value in the normal distribution is larger than x. Behind the scenes, I'm just using Python's SciPy survival function to calculate this probability. So basically, if the probability of something being greater than x is low, that means that x is pretty big, right, compared to the rest of my data. So we want the anomaly score to reflect that and be large. So that's why the anomaly score is the complement. So you might be curious what these two parameters here are, window size and step size. So to determine the Q function, you need to specify the mean and standard deviation of the normal distribution. And these are determined from a sliding window of this time series. So the size of that window is window size. As for step size, note that we have a sliding window, right? So we don't necessarily slide every single new time step we encounter. Instead, I'm saying let's just slide forward every step size many time steps. Feel free to play around with different window size and step size parameters. I didn't choose these under any kind of optimization. I just kind of chose them randomly. So you might be all like, why bother with a sliding window, right? Why don't I just use all the data to determine the mean and standard deviation? Well, the problem is that might not be feasible in online settings. So after running get anomaly scores, I can now plot the time series versus the anomaly scores. And note here that I'm actually skipping the first 50 time steps for the anomaly scores. And that's because initially there's very little data to work with for the mean and standard deviation. And in turn, the anomaly scores might be a little wonky at first. So here I'm going to go ahead and artificially inject an outlier and just see what happens. So I make a big spike occur here at time step 100. And you can also see that the anomaly score also hits the max of 1 at time step 100. All right, so right here is where I planned on us having a 15-minute break. The IPython notebooks I went over, once again, can be viewed as read-only on GitHub if you wish. If you want to play around them, you can pull this image and build it using these links. If you have any questions about how to install them, please shoot a message to Ian. We're going to go ahead and now start a 15-minute break. I need some water, use the bathroom, whatever, get a protein bar, and we'll reconvene and go over some more anomaly detection methods. All right, well, we are going to continue this tutorial. Hopefully everyone has had a chance to use the bathroom, get a snack, so on and so forth. So previously, we talked about STL and using its residuals as a way to find anomalies. And now we're going to actually talk about SARIMA models. So some signals may exhibit short-term autocorrelation that we can try to account for. I'll move on to a popular family of models for time series forecasting, which are autoregressive and moving average models. Now, these models assume that the process generating the time series can be broken down into a weighted combination of past values of the time series and a combination of noise to the time series. So on the left-hand side here, we have a difference. That's the output at the current time t and a regression onto the past p outputs. And on the opposite side, supposing we block out the MA part, we have this epsilon at the current time step, which is the noise signal. In the simplest case, estimation of the pure autoregressive model can be carried out with ordinary least squares. If we unblock the MA part, moving average models are more difficult to estimate because we observe like these y values, but these epsilon terms are unknown. Now, ARMA models are often referred to by their order. So a model with one autoregressive term and two moving average terms would be called ARMA 1, 2. This simply means that P, right here, P is 1 and Q is 2. In time series forecasting, low order models tend to be preferred for simplicity. And these models assume that the underlying process is stationary, so they can't be used directly to model time series exhibiting seasonality and trend. So to remedy this, one would typically apply one or more rounds of differencing, and this leads to ARIMA. So we talked about differencing, right, and experimented with it in the first half of our tutorial. If the signal shows an approximately linear trend, differencing once will help remove it. And when we difference once, that means we have differencing of order 1. A second round of differencing can help eliminate quadratic trend, and that's differencing of order 2. So now, when we talk about the order of an ARIMA model, we have three things: P, D, and Q, wherein P and Q refer to the AR and MA order as before, and D specifies the order of the differencing, or the number of times that you difference. An additional extension to this family is SARIMA. So now SARIMA includes long-term, seasonal, autoregressive, and moving average terms, as well as seasonal differencing. So in that case, we have another set of parameters. So we have the PDQ as before, but we also have big P, big D, and big Q, which describe basically the same things as little p, little d, little q, but correspond with seasonal versions of them. And little s here is the periodicity. So optimal parameter selection for these is not straightforward and typically involves applying various statistical tests and looking at a lot of diagnostic plots. But there are some libraries out there that can kind of help you make these decisions. So we're going to play with Python, auto ARIMA here in exercise 5. So I import a bunch of libraries for the task, and you will notice here that it imports something called Pyramid ARIMA. And this is a nice library to help us determine the parameters in SARIMA in a smarter grid search-like fashion. And Pyramid is the Python equivalent for auto ARIMA in R, which basically does the same thing. I just prefer to show it in Python with these IPython notebooks. So I'm also going to use RPy2 here for some trend tests. So now I'm going to load a data set for Australian total wine sales and plot the data set. So the questions here are, 1, do we need the S part of SARIMA, right? In other words, is there evidence of seasonality? So I go ahead and plot the autocorrelations and actually see some evidence of seasonality with a periodicity of 12. And if you're not entirely sure on the periodicity, you could always look at the periodogram, or you can try that find frequency function in R. I don't show that here, but you can look at exercise 1 on how to do that. Now the next question is, do I need the I part of SARIMA, right? In other words, do I need a difference due to trend? So remember, before we were looking at stochastic and deterministic trends in exercise 2, where differencing helps us get rid of stochastic trend and detrending helps us get rid of deterministic trend. So running the augmented Dickey-Fuller test, I get a p-value greater than 0.05. So we might have stochastic trend. And then the next question is, do we have deterministic trend? So that means we need to run the Cox-Stewart test, which I run in R and get a p-value of less than 0.05. So there is deterministic trend. So remember, the hypotheses order is different between the augmented Dickey-Fuller and the Cox-Stewart test. So to remove deterministic trend, we need detrend. So first, once again, we find a line of best fit. We subtract this line of best fit from the time series. And we use the Cox-Stewart test on the detrended data, and the p-value is 0.08272. We fail to reject the null hypothesis. The null hypothesis is that there's no trend. If we run the augmented Dickey-Fuller test for fun, we see that there is still possibly stochastic trend. But honestly, that's to be expected, right? Detrending is not meant for the stochastic trend. Differencing is meant for it. So how many times do we need to difference to remove it? So now I create a data frame for the detrended data set. So this has the deterministic trend removed, but not the stochastic trend. I do some first order differencing here using shift from pandas and apply the augmented Dickey-Fuller test on here. And we see that there's no stochastic trend. So differencing once is enough. So what does that exactly tell us about SARIMA? Well, that tells us that the little s parameter, which is the periodicity, should be 12 because of the seasonality, and that I, which is the differencing order, should be 1 if we apply SARIMA on the detrended but not yet difference data set. So here in cell 15, if you're following along, this will take about a minute to run on my computer, so don't be alarmed if it takes a while to run on yours. We know that D is equal to 1, and M, which is the periodicity parameter in the library, I know I call it S, but in this library they call it M, is set to 12. And I set seasonal to be true to indicate, yeah, there's seasonality. So how do we choose the rest of these parameters? Well, we perform a grid search over the remaining parameters using some kind of performance criteria, like AIC. The AIC is an estimator of the relative quality of statistical models for a given set of data. It basically quantifies, 1, the goodness of fit, and 2, the simplicity of the model into a single statistic. So when comparing two models, the one with a lower AIC is generally better. So for example, suppose I have ARIMA 313 and it offers a better fit than ARIMA 213, but that fit is not worth the loss in simplicity imposed by the addition of more AR legs. So you can basically switch to a different information criteria in AutoArima, but by default, it's going to use AIC. We can choose to initialize some of the parameters and also set limits on how large they can be. So enabling stepwise means we're going to use a smarter version of grid search. And you can understand a little more about how that smarter version of grid search works in a paper reference that I include in a tidbit section at the end of this notebook. If stepwise is disabled, we're going to be using traditional grid search. Sometimes AutoArima will try out a combination of parameters that also won't converge. So by setting error action equals ignore, we can just proceed to the next combination of parameters directly without erroring out. Also, a lot of warning messages come from stats models, which is what AutoArima is based off of. So I'm going to suppress those warnings by using suppress warnings equals to true. And I also print out the results. You can see all the kinds of parameters that it's trying out and the AICs. And we see that here that it chooses little p 3, little d is 1, little q is 0, big P is 1, big D is 0, big Q is 1, and S equals 12, or M equals 12 in this case, gives us the best AIC. So this means we have 3 AR terms. So that's why we have these 3 AR coefficients. We differenced once. We have 0 MA terms, so we have no MA coefficients. We have 1 seasonal AR term, so we have 1 seasonal AR coefficient. We have no seasonal differencing. We have 1 seasonal MA term, so 1 seasonal MA coefficient. And sigma 2 is the estimate of the variance of the error term. So you can read more about the AIC and these other statistics like LB, JB in links at the tidbit section below for sake of time. So we have identified the model order, the P, D, Q, etc., but now we need to estimate the parameters, right? If we go back here, whoops, we go back here, we have like these thetas and these phis. Oops. And that's what we have to work on next. So we need to estimate the thetas and the phis using maximum likelihood estimation. So basically here, I set the first 125 points to be the training set to determine those coefficients for AR and MA terms, and say like, oh, like the remaining 50 something points is the test set. And here I plot the performance solely on training data here. And the predictions are in blue, the orange line is the data, and it goes longer than the blue line, right? Because we are only plotting the performance of the model on the training data first. So now let's see how our model does on test data. And we have to be careful because the longer we forecast out into the future, the worse it typically becomes. It's a good idea to do incremental training. So let's forecast 50 steps into the future. And here's how the model performs on the test data. And we get the mean of the forecasting error over just the second half of the testing window. Why I'm going to do this the second half instead of the full testing window, I will show you in a second. Now let's add more data to the training portion. Let's add 25 of the 50-ish testing data points. You can add that to the training pile, and you can think of this as like moving ahead in time, assuming that the testing data was data we had not yet seen until this point. We then plot the predictions on the quote-unquote unseen remaining 25 test points. If we get the mean error of these test points, the error is way less than before. So incremental training is pretty important, and that's honestly how often you want to incrementally train is probably based on user choice. So how are we going to determine anomalies given SARIMA? Well, there are several ways this could be done. One way is we could plot confidence intervals and say that a data point that goes outside of the confidence interval is an anomaly. And another way is to make use of that sliding Gaussian window we played with in the previous exercise with SDL, but use it on the forecasting errors. There are probably more ways you can think of to do this, but those are some starting points that you can try out. Once again, here's some tidbits at the end, like the page for pyramid, more about each of those tests, and also automatic time series forecasting, the package by R, for R by Heinemann and Kandekar. Back here. Awesome. So we have looked at STL for decomposing time series into season and trend components. We have also looked at SARIMA, where we analyze autocorrelation plots and use trend tests and grid search to choose parameters. Here, we're going to look at perhaps a more flexible approach based on an additive regression model. This is the model used in Facebook's profit library that is built to be easy to pick up and use for non-experts. So profit uses an additive season and trend decomposition, but also incorporates contextual variables to capture holidays. So the trend component is modeled piecewise by linear or sigmoid shaped saturating functions, allowing like an analyst to incorporate prior knowledge about capacity. So for example, you could say the capacity could represent the population of an area. Change points, or like concept drifts, right, in the trend can be manually specified or automatically inferred. The seasonality component is modeled using Fourier series with a prior to control for smoothness. And this model is built in the probabilistic programming language STAN and uses parameters found by map estimation. You can also adjust this and use MCMC instead. So this type of model, thankfully, naturally handles missing data. And this is because the model is a regression model in continuous time. So a good parallel would be like a linear regression y on x, where a missing value would simply mean we don't have data at some particular x. This is no problem for a regression model. So we're going to go ahead and play the Facebook profit using Python 6. So here I'm going to load all libraries, including the Facebook profit library. I am going to load a data set and plot it. And then I'm also plotting the autocorrelation coefficients. And as you can tell, when it starts to repeat itself, it's 24-hour or basically daily seasonality. So the process for using profit is very much akin to what you might have seen in scikit-learn if you have used it before. You create a model, you fit the model, and then you test the model. So when instantiating this model, there are many parameters you need to take into account. So you can click on this link here for very detailed descriptions of those parameters. I'll give a condensed description for now. So first off, there's growth, and that can be logistic or linear. And use logistic if you know that there's some sort of carrying capacity in your data set. So our data set actually here involves conversations between customers and chatbots, specifically the topic of gift certificates. This chatbot helps answer questions for customers of an airlines company. So basically they're like, oh, how do I buy a gift certificate? And this chatbot can help answer that. So technically there's no limitation on this carrying capacity. So that's why here I'm saying set the growth to linear. Not shown here is change points, which basically would be a list of dates. You can include a list of known change points. If not provided, Profit will automatically try to find them if it's something that shows up in your data set, which honestly in this case, maybe not, maybe a little bit at the end. I basically don't include it because I want Profit to do it for me. Here I say, yeah, there's seasonality and set daily seasonality to be true. There's actually other parameters like yearly seasonality, monthly seasonality. You can, if you don't specify them, they will just be set to auto and they will determine for you if those are there. Here's the seasonality mode, which you can say is an additive or multiplicative seasonality. So remember, additive is typically what you're probably going to see. Multiplicative means that the amplitude of the data of the oscillations is related to the mean of the data. And we don't really honestly see it in our data set. So profit models require a very specific format for their input. Specifically, the columns have to be listed as DS for date and Y for the value. So basically that's all that I'm doing here. I'm renaming the columns to that specific format. I choose the first 7,000 points as training data and the remainder as testing data. And I show head and tail. And tail is like head, but it shows the last 5 rows of the data frame versus the first 5. So now I fit the model to the training data, And note here that there is this warning, disabling yearly seasonality. It's automatically turned off because it's realizing that my time series doesn't have more than 1 year's worth of data. So it can't really tell if there's a yearly seasonality. There's not enough data to be able to determine that. So I create a data frame with dates for the trained profit model to predict over. It includes the training data dates and the testing data dates. And although we use linear growth, if we had used logistic growth for a different data set, we can set the max and min here in the commented out portions. So I make my forecasts here, and the result is a data frame where we can obtain the forecast y hat and the upper and lower confidence intervals using y hat upper and y hat lower. So here's, I'm just showing you y hat. First, I'm going to plot the components of the model because remember, Facebook profit is a decomposition method, kind of like SDL. So here you can see the trend component, and it definitely shows this increase at the end, right? And this actually makes sense because remember, our data set involves the number of times people talk to chatbots involving the topic of gift certificates. And this is a airlines chatbot. So near the end of the year, more people are asking about gift certificates. And that makes sense because that's the holidays, right? People are buying gifts for their loved ones. There's also a confidence interval during this testing portion. We can also see the weekly and the daily seasonality. And this also makes sense, right? People don't want to ask questions to chatbots when they're sleeping or during the weekends. So now we use you can use a built-in plotting function from Profit, but I've never been really that impressed with it. I always think it's sort of hard to see. So I actually use matplotlib to have a better look. And I zoom in on an arbitrary 5-day range. And the actual data is the orange line, and the dark blue line is the forecast. And the light blue fill is the confidence interval. So given this forecasting model, how do we generate anomaly scores? Well, similar to Surima, we could look at the confidence interval and say, if a data point is outside of that, we have an anomaly. But if we do this, as it turns out, there's probably going to be a lot of false positives. Here in this picture, I'm using that first method of, is it outside of the confidence interval? And man, that's just a lot of points. It could also be because we're not fitting it super well. But another alternative is to make use of the sliding Gaussian window we played with in the previous exercise, but use it actually on the forecasting errors. So here you can see the red dots are the predictions, and there's way fewer alarms. And the beginning here has some alarms, but that's to be expected as the sliding window is very small in the beginning, and the mean and standard deviation have not really stabilized yet. So you probably need to ignore the sliding window for the first few time steps. So a few more tidbits here. If you're interested in more details on how Facebook Profit works, especially on how they do concept drift, you can take a look at their Facebook Profit paper. And then there's also the GitHub page for Profit where you can play with it, I believe, and also R if you so desire. All right. So another way to model our time series data is to find a distribution of functions f that could work with our data. If we limit to Gaussian distributions, we would have Gaussian processes. And this means that the function consistent with our data comes from the normal distribution with mean function mu of x and covariance matrix kxx. So let's take a closer look at the mean function and covariance matrix. And typically practitioners will use a flat mean function and spend a lot of time on choosing the covariance matrix. And that's because you can choose it to better fit your data. So this is actually how that covariance matrix looks like. It uses little k, a covariance function, which gives us the power of expression. So if my data exhibits like certain kinds of characteristics, I can choose my covariance function to reflect those characteristics. So for example, if my data is stationary, I could say, let's use a squared exponential kernel function. If my data has periodic behavior, I could use a periodic kernel function. If my data exhibits some trend, I could use a linear kernel function. There is a wide selection of kernel functions to choose from, and in the past, researchers could easily get a paper accepted to NeurIPS by creating new kernel functions for all kinds of characteristics. You can even combine kernels by adding or multiplying them if your data exhibits combinations of these effects. Point is, the kernel function plays a big role in helping you model your data. So once you know what mean and covariance functions to use, you can then take a new input, say x star, and estimate the corresponding output f of x star by choosing f of x star from the normal distribution with this updated mean and covariance. And everything seems, oh, hunky-dory, but actually finding the mean and covariance functions are not as easy as one might think, because as you can see, you actually have to find the inverse of the covariance matrix K here, right, in the middle of these equations. And that gets harder and harder to do the more points you have in your time series. We're not going to go into great detail on this, but that actually leads to people using sparse Gaussian processes for the sake of speed. And I'll give you an example of how to use that in code that we're going to go over here. What's this? 7. All right. So here I'm going to load all necessary libraries, and I'm going to use gpflow. And gpflow is a package for building Gaussian process models in Python using TensorFlow. And I'm going to use rpy2 because this autocorrelation plot function can help us deal with missing time steps, which Gaussian processes can also deal with. So we load a data set here that has a lot of missing irregular time steps. And I'm just going to grab the first 1,000 points just for sake of speed. Now go ahead and plot the time series as a scatter plot, and you can see that there are a lot of gaps here. There's a lot of missing time steps, and it's not very regular. And you can see that the time step difference sizes, which I call delta, here's some stats on that, and you can see that the minimum time step is 2 minutes, and the largest is 1 day, sorry, over here. 2 minutes, and the largest is 1 day and 3 hours. So there's not really that much regularity as in like, oh, okay, once every 7 days we're missing a time step or something like that. So to fit to a Gaussian process, it needs x and y values. And to get these x values, I'm going to use an integer time step index. But if I do that right now, let's say I have 10 minutes between the first observation and second observation, but 3 hours between the second and third. It doesn't make sense to just have x equals 1, x equals 2, x equals 3. There should be a lot more x's between the second and third, right? So I'm going to use the smallest time step size in delta, which is 2 minutes, and fill missing time steps with nans. So then I will create an integer time step called x value. So that's what basically I am doing here. Because I have these integer time steps now, I remove the nan values, and now I have the x integer time steps that actually reflect the time step difference. So I create my x and y values for training the Gaussian process, and now it's important for me to choose my kernel. So to choose a kernel, you might want to check, right, if there's trend or seasonality. I'm not going to go into great detail on this process again because we talked about it a ton already, but note that since there are missing time steps, once again, you have to be careful when plotting the autocorrelations. So R's autocorrelation plotter can deal with missing time steps. You just use NA action equals to NA pass. Don't throw away the missing time steps or your autocorrelations are going to be off. So here's how my ACF looks like. I then take a look at this. You might run around and play with some trend tests. And then with that, you can then create a kernel for your Gaussian process. So here is the kernel that I've decided to play with. And you might note that the most popular out-of-the-box kernel, if you look online, is typically the squared exponential kernel function. And a lot of people tend to just default to it. But in many real world applications, it assumes the data is just a little bit too smooth, and that just doesn't always work perfectly. So without any prior knowledge about the data I'm modeling, I would actually start my investigation with a mat-turn kernel. And it represents a very flexible and general family of distributions and doesn't assume quite as much smoothness as some other kernels out there. So my kernel here is the sum of a mat-turn, linear, and white kernel. And I use the linear kernel because I think there might be a little bit of trend in the middle of the time series. Obviously, it'd be better if I went and used those trend tests. This is just me eyeballing it. I also add this white noise kernel, which allows for uncertainty in observed data. And adding the white noise kernel is almost always recommended for any kernel. So here I decided to train my Gaussian process model and have our Gaussian process predict on the in sample and plot the predictions on the trained data along with the confidence interval. And this is actually somewhat fast to train, but if you have a larger data set, this will be really slow. Gaussian processes have a time complexity of O(n) to the third, where n is the number of time steps you have, right? And if you have an online situation, your time series is just going to get bigger and bigger. So instead of using all of the data points, if we use a subset of the data that represents the full data well, that will actually make that covariance matrix, big K, inverse, easier to calculate. And that subset is called the inducing inputs. And that actually leads us to sparse Gaussian processes. And there are various ways to fit a sparse Gaussian process and determine the best inducing input set and other parameters. But I'm going to use a variational free energy approach, which you can read about in more detail in a paper I've linked in the tidbit section below. And here I am simply initializing the inducing input set Z to be some random 100 points and train a sparse Gaussian process here in cell 15. And the Gaussian process will determine the best inducing input set and parameters when we train it. And obviously, I'm looking at a toy example data set, but if you have a large data set, sparse GPs are the way to go. Here I simply plot the predict the in sample and plot it. And like before, if you want to get anomalies, you can either look at, hey, is a point outside of the confidence interval, or maybe use a sliding window technique on the forecasting error. So here you can look at the GitHub page for GP flow, the way I chose to train, which was using the variational free energy approach, which I will say there's several approaches, but this is probably one of the best ways. This covariance functions reference is great if you're like, hey, I have this kind of characteristic. How do I incorporate that into my kernel? All right, so now we have looked at that. I'm going to look at our next method. Which is RNNs. So given a window of n lag many time steps in the past, a recurrent neural network can be trained to predict a window of n sequence time steps in the future. So we use the multi-step prediction RNN developed in this paper below, in the footnote, which can adapt to concept drifts after an initial period of training and doesn't require non-anomalous training data. So each point in the raw input as well as the raw output is normalized as a pre-processing step. And after an initial training period, the RNN is then trained and tested incrementally to determine anomaly scores. And the anomaly score is computed as an average of the error over the prediction window. And computing it as an average is very important because that means that a short-term anomaly will only affect the score for a short period of time. If the score is consistently large, though, that alerts the RNN to adapt to the new normal by changing its parameters accordingly using a technique called back propagation through time. It's called BPTT in this picture. So in this picture, IT is the input and is fed to the RNN along with WT-1, which is the weight matrix. The actual data is compared to the output of the RNN to compute the anomaly score called AT. Then the RNN's weight matrix is updated using BPTT, given this anomaly score, to create the next weight matrix, the updated weight matrix WT. The RNN is a very complex model, and a lot of fine-tuning of parameters is required. So for example, the choice of N sequence here can greatly affect the false positive rate. The larger N sequence is, the earlier the change detection happens, but the longer false positives will persist after the occurrence of a true anomaly. And I will demonstrate it here in our next coding session. So for these notebooks, if you're following along, it can take a while to train an RNN, especially on a laptop. So I would suggest that y'all just follow along here and then play around with this code at home or on better computers with GPUs or whatever. So we load all necessary libraries. TensorFlow is one of the most famous libraries used for deep learning models, and I'm going to use Keras, a high-level API built on TensorFlow. It is more user-friendly and easy to use as compared to TensorFlow. So here I'm going to load a data set we have seen before that has concept drift. We've seen this guy before, right? When we use the Bayesian concept drift detection library. So I'm going to plot the data set, and now we need to determine our N leg and N sequence, right? So given a window of N leg many time steps in the past, a RNN can be trained to predict a window of N sequence time steps in the future. And we're going to prepare our data for that kind of structure using these functions here, which will output our training and test sets. So let's experiment with that function. This toy example, I'm going to say, let's set N leg to be 3. And then we're going to set N sequence equal 2. So that means we're going to use 3 time steps in the past to predict a window of 2 time steps in the future. So that means that elements of X will be 3 time steps long, and elements of Y are going to be 2 time steps long. And I set the split index between training and test set just for this toy example to be 10. So here are the first 5 values of my time series. And the first element of X train will be those first 3 time steps, and the first element of Y train will be the next 2. I set the split between train and test to be index 10 for the sake of experimentation. So here are the values of the time series from the 10th value onwards. So the first element of X test will correspond to the 10th, 11th, and 12th time series values. And the first element of Y test corresponds to the 13th and 14th time series values. So now the next function. This function is going to help us determine the anomaly scores. So recall that the anomaly score is computed as an average of the error over the prediction window. And here, I define my RNN. So the sequential model is a linear stack of layers, and I can just very easily add layers. So I add 3 hidden GRU layers here. So the unit of computation in a neural network is the neuron, also called a node or unit, and the unit receives input from some external sources or other nodes and determines an output. So you have several choices for these nodes like GRU or LSTM, and GRU adapts more quickly to concept drifts than LSTMs, and that's because LSTMs tend to remember longer sequences than GRUs. GRU is also computationally more efficient than LSTMs as they have fewer gates, and you can learn more about differences between GRUs and LSTMs in a tidbit link below. You can set how many neurons you want in each layer using N neurons, and we can also set our dropout probability for each layer here. Dropout means we're going to ignore some units of computation during training with probability P. So in this case, P is 0.2. So we have dropout to prevent overfitting to our data. We end with a dense layer. And a dense layer is simply a classic fully connected neural network layer. Basically, every input node is connected to every output node. So the network will use a mean square error loss function and the efficient atoms optimization algorithm to minimize that. There's a lot of choices for optimization algorithms, and there's also a link below for how to make your choice. And an epoch is a one complete presentation of the data set to be learned by the RNN. So here I'm going to finally combine everything we talked about, from preparing the data to fitting the RNN, and finally computing the anomaly scores. So that's this entire huge function here. And I fit the RNN here. And the initial training period I set to be 15% of the data. Of course, this RNN has to be incrementally trained to determine the anomaly scores after that initial training period. Here I chose n leg to be 100 and n sequence to be 5, meaning I used the past 100 time steps to predict the next 5 time steps. And each incremental training period, the testing set is 20 time steps long. The number of epochs we set to 10, and every hidden GRU layer has 40 units. So I plot the anomaly scores here. And the spikes correspond to locations of the concept drifts in our data, right here. At the bottom of this notebook, we are going to zoom in to get a better look at the anomaly scores, but let's just wait a moment. Note, here on the left, the scores are not normalized. So you either have to predetermine some sort of threshold or normalize these. Unfortunately, in an online setting, you will typically never really know the max, so you'll have to think carefully about how you're going to do this. For example, you can feed these unnormalized scores to the sliding Gaussian window. So remember how I talked about the effect of n sequence? Here, I'm going to go ahead and up n sequence to 50 from 5. And here, we zoom in on a section of the anomaly scores for the RNN using n sequence equals to 5, right? So the nice thing is that the RNN realizes that a concept drift has occurred. So we'll initially say, hey, there's an anomaly, right? But then the score goes down when the RNN says, okay, this is the new normal. But here, I'm going to zoom in on a section of the anomaly scores for the RNN using n sequence equals 50 instead of 5. So now you can actually see the effect of increasing that. So the larger n sequence is, the earlier the change detection happens, but you might have more false positives. The point is, RNNs have a lot of parameters, and having one tweak, like even with just n sequence, can produce quite a dramatic effect. At the end of this tutorial, we're going to talk about what we can do involving these parameters. But first, we're going to talk about evaluation. So we have gone over a bunch of anomaly detection methods and how to use them, but how do we start comparing them? So we looked to the evaluation methodology used in the Numenta anomaly benchmark. All of the evaluated methods were adapted to produce a score between 0 and 1. For models that produce something like a residual or a likelihood, we use the sliding window Gaussian described at the start. Each method was evaluated with 2 different scoring algorithms. The first is a scoring algorithm introduced for the Numenta anomaly benchmark. So for this method, a window is placed around every ground truth. Detections that occur outside of the window, in other words, false positives, are scored relative to the preceding window. And this scoring algorithm is designed to give partial credit to detections that occur after the end of the window with a decay controlled by a sigmoid function. And the size of the window was determined by Numenta to be 1/10 the length of a time series divided by the number of ground truth anomalies. In reporting the overall score, the values for positive detections and false negatives are added up, then rescaled such that a perfect detector would score 100 and an algorithm making no detections would score 0. And the relative costs of false positive versus false negative errors can be tuned based on domain considerations. The detection threshold is optimized over all datasets within the corpus and the best achievable scores reported. A simpler approach was also considered, where the time series was divided into non-overlapping windows and evaluation was carried out as if this was a binary classification problem. A window is considered anomalous if it contains a ground truth anomaly. To optimize for the windowed F-score, we minimize the total number of errors where false positives are assigned a smaller weight to prefer detection in the case of a tie. Optimization uses a grid search over detection thresholds and false positive weights. And experiments showed that results were not overly sensitive to the exact weight. So now I will proceed to briefly explain our offline experiments and answer the question of which method is more promising given a characteristic. So for our experiment, every characteristic has a corpus of 10 datasets. Some datasets exhibit multiple such characteristics and can appear in multiple corpora. And some of the datasets we use come from the Numenta Anomaly Benchmark repository in the link below, which consists of pre-annotated datasets across a wide variety of domains. Annotation instructions for ground truths are also available in that below link. For seasonality, trend, and concept drift corpi of datasets, any missing time steps were filled using linear interpolation. For the missing time step characteristic corpus, we either choose datasets with the missing time steps already, or we randomly remove data points from datasets with originally no missing points to generate the corpus. So let's walk through an example with the F-score windowed method. So recall that we chose the anomaly score threshold based on what returns the minimum number of windowed mistakes across all datasets comprising the concept drift corpus. So in this slide, we consider the anomalies as determined by a method called HTM. I didn't cover it in this tutorial, but it is a special kind of neural network. The RNN and SARIMA for one of the datasets in the concept drift corpus. The HTM and RNN appear to perform quite well, capturing the initial spike and the first few concept drifts. SARIMA, however, suffers being extremely sensitive to noise and also unable to quickly adapt when a concept drift has occurred. Recall that a concept drift should trigger an anomaly, but an adaptive system should quickly determine that a new pattern of behavior has occurred and is the new normal. So in our experiments, for seasonality and trend, decomposition-based methods perform better than the other methods we have discussed. So recall that STL breaks the time series apart into a seasonality, trend, and residual component, and the residual component is what is analyzed for anomaly detection. Profit is also a decomposition-based method, but a component specifically built for seasonality and trend. The integrated portion of SARIMA allows for differencing between current and past values, the I, right? Giving this method the ability to support time series data with trend. And SARIMA's performance with seasonality, well, maybe due to the fact that seasonal versions of the autoregressive moving average and difference components are considered. For concept drift, both the F scores and NAB scores suggest that more complex methods are necessary, such as the RNN, neural networks, the HTMs, and also Profit. Recall that Profit can automatically detect concept drift, although unfortunately you will have to tune a parameter to adjust how sensitive the concept drifts you want to be. And a word of warning with the RNN. You might initially get mediocre performance, but this is most likely because of the presence of false positives. If your end sequence is too large, false positives will persist after the occurrence of a true anomaly. As for missing time steps, we are still currently working on this, but we noticed a great lack of anomaly detection methods that can handle them innately. Most papers tend to just brush this detail away and require some form of interpolation first before you can apply them. So this is definitely an area for future work. So what about evaluation strategies, right? So NAB scores reward early detection of anomalies. For NAB scoring, a window is created for every ground truth anomaly, with this anomaly right in the center of the window. And if the prediction is within the window, But before the actual anomaly, the reward is even greater than having the prediction on the exact same time step as the actual anomaly. So keep that in mind. Compare that to our window-based F-scores where the entire series is divided into windows. So there is the possibility that a predicted anomaly can be rewarded under NAB, but be punished under the window-based F-score system. In sum, I would say that our F-score scheme tends to be more restrictive with its detections to NABs, reducing false alarms, but it also doesn't reward early detections like NAB does. So what you choose is dependent on the needs of your application. So as there is an ever-expanding library of anomaly detection methods, we save users time by surfacing the most promising methods. And the definition of what it is an anomaly is highly subjective, so human input is essential in the decision-making process. Although we automate as much of the process as we can, such as determining the presence of characteristics, narrowing down the search space for anomaly detection methods, it's not advisable to completely remove the human element. So for every selected anomaly detection method, its predicted anomalies could be given to the user to annotate, right? And based on that decision, the parameters for the method could be tuned to reduce the error. But parameter tuning is very dependent on the anomaly detection method. Could be simple, like for example, if a method produces an anomaly score between 0 and 100 with an anomaly threshold of 75, the system could raise the threshold to reduce false positives. And using this feedback, the system learns to minimize false positives for the user data. However, there is a plethora of anomaly detection methods, each with their own parameters. I mean, just look at the RNN. What a nightmare. Determining how to tune these parameters for every possible method is just not feasible, especially as the number of anomaly detection methods increases. Many methods already output an anomaly score, or can be easily converted to produce such an output. Thus, we tune the anomaly scores instead of the anomaly detection parameters for the sake of generalization. And we decide to tune based off of two concepts. So when an anomaly detection method predicts an anomaly in a time series, these predictions tend to occur in clusters, like in this time series. So on time step 4200, there's the spike, and the arbitrarily chosen detection method, which in this case is Facebook Profit, detects this massive cluster of anomalies, which are the yellow circles. To prevent alarm fatigue, we keep the first detection in the cluster, but ignore remaining detections in the cluster. And the user can specify how many time steps are to be ignored following a detection. So given a predicted anomaly, we multiply that many user-chosen steps of anomaly scores following the predicted anomaly's time step by a sigmoid function, the error function, to briefly reduce the anomaly scores of clustered anomalies. Concept 2. So in the left figure, suppose the annotator disagrees with the predicted anomaly, the yellow circle, around time step 100. A very similar pattern occurs in the same time series later, around time step 500. And the anomaly detection method predicts an anomaly in a similar location. So it's pretty likely that the annotator will also disagree with this predicted anomaly. So we desire to prevent future predictions that would waste the annotator's time. Therefore, we determine similar chunks of the time series when given a false positive by using Muin's algorithm for similarity search, also called MAS. So MAS takes a query subsequence, which is simply a contiguous subset of values of a time series. So MAS takes a subsequence and a time series, and then it returns an array of normalized Euclidean distances and the indices they begin on to help users identify similar or dissimilar subsequences in the time series compared to the given query. So similar subsequences will be called motifs, and dissimilar will be called discords. So for every detected anomaly that the annotator disagrees with, a query is created by forming a subsequence of the time series of user chosen length with the detection in the middle of the subsequence. And we reduce the anomaly scores corresponding to these motifs by multiplying them also to a sigmoid function. So the more similar the query is to the corresponding motif, the greater the reduction to anomaly scores. The minimum weight multiplied to the anomaly scored is set by min weight, and how quickly the sigmoid function converges to 1 is determined from the max discord distance from the query, max distance, also determined by virtue of us already using mass. So let's consider a quick visual example. So on the top left is a time series with the yellow circles as predicted anomalies. So a no anomaly score tuning is applied. On the top right, we apply just concept 1, where clusters are removed. On the bottom left, we apply only concept 2, where we remove instances similar to where a user previously disagreed with the predicted anomaly. And on the bottom right, we apply concept 1 and 2. The number of predictions is greatly reduced, and most crucially, we don't miss the ground truth anomalies, which are the 2 red X's. The exact time series right here is what we're going to play with in our final coding section. So applying these concepts can save a lot of annotator time, and we demonstrate this using progress plots, where the x-axis is the fraction of annotations already done, and the y-axis shows the fraction of annotations left. So in the worst case scenario, every annotation only reduces the number of remaining annotations by 1. So then we would have y equals to 1 minus x, which is this orange line. This would mean there are no anomaly detection clusters and no similar instances of confirmed false positives. So in this figure, we show the progress plot for a time series called art load balancer spikes using an anomaly detection method called GLIM. Without removing clusters and applying mass, 117 predictions would need to be reviewed by annotators. Using both concepts, only 29 annotations are needed in total, reducing the fraction of needed annotations by almost 80%. As an example of concept 2, suppose the annotator disagrees with the first prediction made by GLIM. Mass determines there's a similar subsequence further along in the time series containing a prediction that's not yet tagged, and lowers the anomaly scores corresponding to the subsequence. So instead of 117 annotations being reduced to 116 after a single annotation, we have 115 remaining. So we're going to go ahead and play with these two concepts in Python. This is going to be our final coding exercise. So I'm going to grab a time series from Numenta, and this is pre-annotated, so we already know the ground truths, of which there are 2, which are right here. Here's their values and their timestamps, and this outlier column is 0 if it's not an outlier and 1 if it is. And I'm going to arbitrarily choose an anomaly score threshold and an anomaly detection method, which in this case is Facebook profit. I already have the anomaly scores produced from this method, so I'm just going to load them up using the Python library joblib and obtain predictions by comparing the scores produced by profit against this threshold. And I plot the time series in blue, and the red crosses are the ground truth anomalies, and the yellow circles are the predicted anomalies produced by profit. So concept 1 involves removing clusters of predictions. So after a prediction is made, we multiply TS affected many scores following this prediction by the error function. And this function creates the weights that we multiply the scores by. And here's version 1 of our human in the loop algorithm, and it only contains concept 1. It iterates through the predictions, reducing anomaly scores briefly after every prediction and updating the prediction list after the update to the scores. And we apply this algorithm to our current prediction set and arbitrarily set TS affected to be 2% the length of the anomaly scores or the time series. So without concept 1, we had 119 predictions. With concept 1, we are reduced to 10. We can see the number of yellow dots, the number of predictions, is dramatically reduced. There are no clusters now. Now we're going to experiment with concept 2, where similar instances of disagreement by the annotator should be removed. And the weights are produced by a sigmoid function where these k and b are parameters that are dependent on how similar the instances of disagreement are. So to find similar instances, we use Moulin's algorithm for similarity search to find similar subsequences, otherwise known as motifs. So we use the mass.ts Python library to do this. The GT's parameter for this function, we go down here, oh, it's long, here, GT's, is set to unknown default, and this represents the fact that we don't actually typically have a pre-annotated time series. This GT just stands for ground truths. So typically, user input would be required on predicted anomalies. However, fortunately, in this instance, we do know the ground truths, so I will set GTs to be a list containing those two ground truth anomalies when I actually use this function. So I say we agree with the predicted anomaly if it's within an arbitrarily chosen acceptance range of 25 time steps of a ground truth anomaly. And that 25 is honestly user chosen. If the user disagrees with the predicted anomaly, or we are not within 25 time steps, we create a subsequence with a disagreement in the middle. Mass then returns an array of normalized Euclidean distances and the indices they begin on to help users identify similar or dissimilar subsequences in the time series compared to the given query. So the minimum weight multiplied to the anomaly scores is set by min weight, which is user chosen. I chose 0.95. And how quickly the sigmoid function converges to 1 is determined from the max discord distance from the query, max dist, which is also determined by virtue of us using mass, because we have all of those Euclidean distances. So using max dist and min weight, we can determine the parameters for the sigmoid function, which creates the weights. We reduce the anomaly scores corresponding to these motifs by multiplying them to that sigmoid function. And the more similar the query is to the corresponding motif, the greater the reduction to the anomaly scores. So without concept 1, we had 119 predictions. With concept 2, we reduced to 52. So here we plot those 52 predictions. Finally, we combine concepts 1 and 2 to create this final human in the loop algorithm function. And this reduces the number of detections to just 8. And I crudely print out yes when there is a prediction within 25 steps of a ground truth. And both instances are picked up. And you can also see the final product in this plot. And this is a big reduction from the original prediction list. Point is, there's a lot of anomaly detection methods out there, and parameter tuning can be a bit of a nightmare, especially since there's so many different parameters for every anomaly detection method. You could go about, with an extensive grid search, but that will take some time. So maybe it's better to look at something like the anomaly score, where you kind of edit it based off of what the user thinks an anomaly is, which is a very subjective task, right? Depending on the domain, something that one person thinks is an anomaly might not be for another person or a different domain. So these are steps that we think could help with something like this. So in summary, the existence of an anomaly detection method that is optimal for all domains is a myth. Anomaly detection is a hard problem for many, many reasons, of which one of them is which method to choose in an ever-expanding library. And one way to deal with this problem is to determine the characteristics present in the data and narrow the choice down to a smaller class of promising anomaly detection methods. In addition, by employing mass and reducing prediction clusters, we can reduce the number of false alarms, potentially increase evaluation scores, and not have humans tag the entire time series and instead just tag like a portion of predicted anomalies. All right, well, thank you. And I hope that this tutorial was of some benefit for you. Once again, I didn't cover all the characteristics out there or all the anomaly detection methods, but I wanted to make sure that I covered some very important ones that you will probably commonly see, and then some potential ideas for how to deal with the fact that a lot of anomaly detection methods out there have a lot of different parameters, so tuning it can be a nightmare, and how do you deal with all of those false positives, right? So once again, if you're curious about getting the code, you can look at those 2 links that Ian has sent that has the IPython notebooks. And there also should be a link for the PDF of the slides if interested. Thank you.
Thanks, Cynthia, and also Ian. One question for me.
Yeah.
I can see you have a couple of data sets in there. That's all public data sets, or if some other researchers want to test, can they use the data sets, or do they need some ethic approval?
That's a great question. Thank you. So the data sets that are used in the code are actually all available. I provide them as little folders that you can go look at, along with another text document that shows you where I got those data sets from. So all of the data sets are available for you to play with. And a lot of the data sets I actually pull from come from the Numenta Anomaly benchmark repository, which is in the slides. Let's see, all the way back here. Oh my gosh. There is a link here, I promise, is Numenta Anomaly benchmark repository, and you can use that, and it has like around 60 annotated data sets, and it's all there just for you to play with. And so there's no worry about, oh no, do I have to, email someone to get access to the data? Because, oh, here we go, right here, the Numenta Anomaly benchmark repository. A lot of my data comes from here. And some of it also comes from the time series data library. And the nice thing about this Numenta Anomaly benchmark repository is that it's already annotated. And if you're curious about how it's annotated, you can look at the second link here for the annotation instructions, which are very, very detailed.
That's great. Thank you so much.
Yeah.
I'm not sure any other questions from here, because we have some story in the middle. Anyway, that's also first time for me to have the Zoom bomb.
Yeah, it sucks. I mean, it's something that kind of appeared with the rise of people using Zoom because of COVID. So yeah, just a lot of bored people out there. But yeah, if anyone has any more questions, they are free to email me those questions at my email address here. If you have questions about specifically, oh no, this notebook, IPython notebook's not working for me, then please email Ian, who's my boss, and he is the one who helped me distribute these IPython notebooks. It took him quite a bit of time, so thank you so much, Ian. And yeah, thank you.
Yeah, I can see Ian has already posted your slides and also the codes in the chat. So I think, yeah, so participants can find them. I believe they're all very useful.
And there's a Docker file too that you can pull that has all the dependencies and everything, including R and Python pre-installed. So you don't have to worry about trying to figure out how to get the examples to compile. And that link is there as well. You can just pull that image and run it if you have Docker installed on your machine.
Thanks, Ian. Thanks, Cynthia. I'm not sure, is Tim still here?
I actually don't see him. He's not listed as a participant.
No, I don't think.
Okay, if no, maybe we just close today's tutorial because we had the wonderful presentations, two tutorials together. Thank you both again.
Thank you. And whoever recorded this, can you?
I think we have Oliver and another one volunteer. They are very also thanks for them to support us because we have some something in the middle and then just generate another link for us.
Yeah, like if you can get those, videos cleaned up, get rid of the it's not very great material, and shoot me like a link to that video so I can like share it with people who might be interested, that would be really appreciated.
Yeah, sure. Thanks.